Well, see here my attempts. But that approaches the logarithmic integral of ln x, I think. Yeah, let's plot this thing. Make a copy of this. Yeah, I want to make a copy of that exactly. Did the thing just copy it? That's nice. Okay, so plot my approximation with well, x is 8 to, this is still the logarithm, right, to 40. And the lie of the ln of x. Nope, something went wrong. Well, maybe it's not the ln of x. Still doesn't work. This looks like the opposite. I need to take the ln of this. Of course I want to compare with the ln of, no, I want to compare with the li of the ln. Definitely. Or not. No, I don't. Oh boy. Yeah, no, not really. No, it doesn't want to plot anything anymore now. This was the integral of I think the derivative of the EI. Let's plot that then. EI of X. I cannot even remember that anymore. Totally not. EI dips up like crazy. So maybe no, there's no way that's gonna be the ln of X, of course. X is 8, 8, 8. Completely lost it. Unbelievable. Yeah, this one. These two are equal. It's the exponent over x times that. So the derivative of this. Oh, wait. Did I integrate it? No, I didn't. No, this is the derivative. This is the derivative of. I think. Yeah. We integrated this, and then we get, of course, the function that we then should get, because they are almost the same thing, especially for higher values. We should get the integral of this, which is whatever this is the derivative of. I'm going to go back until I see what that is. The derivative of the ln of AEX. So integrate it, I should get that. The ln of the AE of x. Or x is the ln of the upper limit of the, well, the prime number, say. The ln of the AE. Hopefully we can go back now. So I mean ln of the AE. Nobody knows. I mean, is it such a perfect match that we don't see any difference now, or what? 10 plus. Yeah, it is. It's such a perfect match that you can't see it. Wow. Okay, so get rid of the plus 10 again. Do the exp on both sides. So I need the exp of this whole thing. Still on top of each other, I hope. And then the 40 is ridiculous, because now we're going to work with replace x with the ln. So all the x's become ln's. And this is indeed an ln. ln. AE ln. For x is, well, let's say 1000 till so this is the number up till this, the number up till which I want to know the number of primes. And this should be equal to, let's add a million, see if that separates it. 1, 2, 3, 1, 2, 3. Yep. And this should be equal to the LE of x. And then this is my approximation for the LE of x. I did not just click it across. 1, 2, 3. Now the difference becomes way too much. Yep, so you can hardly see it, but if I make this smaller than say 1000, then at some point you should start to see the difference, because it's definitely deviating for the smaller values. Still nothing. Dude, 10. Yep, now there's a spike here. Huge spike. Still hardly visible, so let's remove the view here. Yep. 10 is not working. I think you have to start it like 1000 at least. Still pretty good. But the most important part was not just approximation, but that it is always larger than that. So if I subtract this from each other, now we should get something that is positive. No, it is not. It becomes negative. You gotta be kidding me. What the hell, man? What the hell? Impossible. So disappointing. But now I think about it, this is a prediction for the number of primes, and we are less than one off. That's pretty damn good. Let's go to 1 million. Let's see if we are approximating it with 2 minus 1. Oh no. We went negative and then it goes off the charts. Okay, let's add 1. So my formula, let's add 1. I'm gonna add 1 here, plus 1. It would never become negative, never. That looks pretty positive. Oh, it's definitely incredibly positive. Oh, I did something wrong now? No, I didn't. Oh yeah, I added a plus 1 inside the exponent, so that was nonsense. We must do 1 plus the exponent. Let's do just 1 plus the exponent. Now that's better. So this is definitely positive, so we are interested in if this becomes negative at some point. For, let's say, 10,000, which is already ridiculously small. And apparently it doesn't. Yeah, very nice. So this is the amount that we, if I use this formula, then this is the amount that we would allocate too much. 3 bytes, oh no, well 4 bytes. And at 100,000 we allocate 2 bytes too much. That's super good, isn't it? But then, of course, if you start to ask really large things, like all the prime numbers up till 1, 2, 3, 1, 2, 3, I will never go any larger. It's 10 to the power 12. Right? Yes. So then you allocate a terabyte, and you accidentally allocate, I don't know, to 20 megabytes too much on the terabyte. So that's extremely good. I like my approximation. Unfortunately, the Li is also too big. Already, all by itself. So this is an approximation of Li, and I was thinking, well, maybe I should make an approximation for the actual function. I don't know how to type pi here. The number of primes below x. Can I do that? I don't know. No, I'm starting to wonder, how important is my super weird vector that I made up here? Because this looks so clean. If I just remove this, what happens? Let me copy it before I destroy this. No, then we allocate not enough. So it is important to stay positive. Then we do some reasonably smaller thing. Still negative. Yeah, so let's write a program that calculates the exact number of primes up till a given value. Let's say hello Gabriel. No, a billion. I should be able to allocate that. Let's say standard vector of the number of primes. All the way up to 1 billion. Can I allocate that? Just a gigabyte times whatever I've put into here. I think an int cell fits. I'll make it an uint. Just a little bit larger. Oh, okay. No, that worked, I suppose. So now let's pass that to that function. Calculate primes. And then every time we push back a new result, then the number of primes becomes one more. So I should just do plus plus a number of primes. Now what? I think I'm just going to fill things here also by hand. This is correct, right? So this means that the number of primes up till and including 2 is 1, and up till including 3 is 2. Well, up to including 1 is 0, and up till including 0 is 0. And then of course 4 is also 2. But I shouldn't have to do that. The next time we find a prime, oh wait, actually I did find a prime already, yeah, 5, you push back 5, okay. Let's do this one as well then. Oh, this is 3. So now the next time I find a prime, I want to fill in the 3 all the way up till that next prime that I found. So here we get 4 into k as the previous prime, which is result dot back. That's the last one that we pushed, so that would be 5. Push that there. Now 5 was 3, so we can start after that, as long as k is less than this prime. And then we can say that the number of primes up till and including k equals the current knob. Then we increase the knob and we push that one. And if that was the loss of it, yeah, well, I might as well do this, I guess, just not +1. Wait a minute, so if I do not +1, then K is K is simply 5. So I don't have to do this one. And then here we have that again. Okay, so the index is always less than prime. And prime is less than or equal max value. Therefore, K is less than max value. Therefore, if I pass that value here, then that should be safe. Let's print out a view to see if that is correct. Make. There's the first prime, second prime, third prime, fourth prime, and then 11, 13, 17, 19. No, looks okay. So the total number of primes up till and including 97 is 25. So now I need to make an approximation that, that's why I have to run over all the numbers. No, that's not how it works. I is 0, I is less than number of prime size. No, not calc. Just have it. I have it calculated. The number of primes is now simply stored in this array. Oh wait, no. I want to go. I want to write a function. Yeah. It's okay. Calc. Calculate the number of primes as a function of I. That's the trick then. Call this n, just an integer. Let's start at, yeah, really doesn't have to be that correct for small numbers. I want to, for now, start at 1000. And then assert that np that we return is always larger or equal to the actual number of primes. And I want to calculate just a maximum error, I guess, or the maximum percentage maybe. Kind of both. I guess both. So the absolute error and a relative error. So the maximum of both. And they are both positive, so we get larger, and then we get standard max. Of the previous value and some new error. I can calculate that. Absolute value is, well, this is larger, so it's np minus number of primes n. And this is the relative error, that would be absolute error divided by the number of primes. Also positive. I don't know. If I subtract this, nah. Gonna do that. Then I cannot compare it anymore. Let's cast this thing to just cast it to int 32 type. For the sake of I have a better idea. Diff is that. It would work, right? Diff is larger than 0. Now it's signed. Which then makes max absolute value error, I mean, must be that. And here I can use a float, I suppose, for the max relative error. And this must then be cast to a float. Otherwise the standard max doesn't work. And you have to write this. Yeah, then for start, I guess I'll just use the function that I just came up with. Because at least it should work. Well, let's begin with like that, you know, and then see that we assert somewhere. What? Of course, there are more than 100,000 primes. It's already saying that. Yeah, that's more than 100,000. 5 million. This should return 5 million and it'd be negative. It's 100,000 minus that, negative, assert. Assert does not assert. Why does it not assert? Let's just try a few things out because I'm stumped. Nope, that was not it. No. We never get there. We never get there. Is it larger than an int? Nah. Oh wait, an int is no, it's not larger than int. Or is it? Are we even compiling this thing? Looks like it. Oh, I don't have debug output. Seriously. Yeah, and I don't. It was released, so it didn't have a search. Oh, well. That takes considerably longer than before. -1, seriously? Yeah, of course, it just goes down slowly until we reach -1. Hmm. I'll do 99709. Oh, the diff here, 709. Yep. I have to do that one bigger, and that would be one that's below after that one. That one. 721. Yep. Very good. So we should get past that point if I use my formula, which is involved. Double log n is standard log n. Oh my god, how do I do that? Start copying this back. I need to calculate this. How do you do something to the power 1.6? Okay, I'm stupid. I'm being very stupid. I don't know any. I'm gonna ask ChatGPT. Or I can just think and then maybe revive a few brain cells. So I want to calculate a to the power b. Well, that is equal to oh man. I don't know anymore. I've become officially senile. There is a POW. Base exponent, seriously. A log of log n minus 1. That's the log, and the power of the base, comma 1.6, where the base is 1 divided by log n minus 4. Hi J Mellon and Nix. No, I didn't. Is this correct? I guess we will see. That's slow. Hey Shy. Well, I guess it doesn't assert, but it takes a long while. Okay, how far do we go? 1, 2, oops. 1, 2, 3. I think only till we are already at 1/3 now. I think I should set a modulo to 10,000 because, and then maybe compile it with optimization. Only halfway now, but well, let me check. Let's let it run till the end. Yep, that worked. Let's go back to, I want optimization, but I also want debug output maybe. Just give up on the debug output. I do want I do want optimization, but also a search. And I think I have that by default. Not sure. I'll call it beta maybe. Beta is not known. No. Fuck me. This is so annoying. It's even my most favorite answer here. Beta test. I call it beta test. Dat is with optimization and debug output. Mine is a no debug output. Yeah. So that. So I should have that working by default. Just typed it. Yay, better this works. Yeah, okay. There's the O, and then I don't see a no debug. Nevertheless, let's try to make it crash. I don't have debug output anymore though, but I want to test if this assert still works. How do we do that? So let's change this into cout. And I wanted to make it 10 larger. And I want to test if we have assert. The assertion works. Now let's see if it indeed is faster. The first 2.7 seconds are needed to generate the primes. That definitely looks faster, at least 10 times faster. Although but no, okay, this one runs to 100 now, so it already passed the half. View, and then all of that without printing what we wanted to know, namely the max absolute error is max absolute error, and max relative error is the max relative error. Maybe I should reduce this a factor of 10 because it's just too slow still. Or I can make, I can actually just make, say, 1,000 probes and slowly increase it. Relative error is infinity. That's not good. Absolute error is 50 megabyte. That's not good. That happens probably somewhere in the beginning where must be division by 0. No, that's not possible. Strange. Let's hope that it happens before this, because let's start with some that which is 10 times faster again. At the very last moment, it's 0. Yeah. The reason is that I don't fill in everything above the maximum value, I think. Above the maximum value. Till the maximum value. Just have to do that here, I'm afraid. Should be the same. I'll use number of primes, but no, that's nonsense. What am I doing? Number of primes? Oh, wait, that's correct. Relative error 7.7%. It's pretty bad, but probably also from somewhere from the beginning. Let's speed it up extremely much, because we're going to need that in the end. I don't need to test this for every number, I just need to test it for 1,000, and then let's say we make steps like It's not too much. Let me see what happens if I do it times 2. That's fast. Fast enough. The output is not the same though, which is strange, but okay, maybe we skipped something. Yeah, I'm not happy. I'm not happy at all. This is you could even completely skip over this. So now it's complete nonsense. Should be 4094. I just want to test this evenly spaced 1,000 times, say. So, evenly spaced means just use a double and then round it down or something like that. Multiplied with the 1,000th root of whatever the factor is that we have here. And we do a vague attempt in that direction. So I want to do the double of the step factor is the 1,000th root of number of primes divided by 1,000. I don't need doubles or whatever. Comma the 1,000th root, so that would be 0.001. Hopefully that works. And then we have the double S, so is a step. Oops. And then we do that, still print every 1,000. And then the step must be increased. So the S is multiplied with SF. And the step is the rounded down version of that. I think this works. I'm not convinced whatsoever. Nope. That's considerably more than 1000. Still everything, it looks like it. What am I doing wrong here? Step never going to be bigger than 2? Oh, I'm an idiot. Wait a minute. I'm multiplying 1. No, I'm not an idiot. Wait a minute. SF must be larger than 1? Definitely. Let's just print it out. SF. Yeah, that was not useful. Zero point 0115 calculator. 1, I mean 0.01158 to the power 1000. 100. Seriously, 100? I think I'm too stupid. Cubans, hey. Yeah, what I want is that we start at 1000 and then we go to something big. I don't know what it was. Probably 100,000 at the moment. And I want to increment. Yeah, see, I just multiplying with this one must be multiplied with, which perfectly works, by the way. If I do, if I use 1.01, that's okay. If you start at 1000, it would even work from 100. Might as well do that then. So I'm going to do forget the step. Still far from the truth. It's kind of strange. Let me print out everything. A lot more anyway. No, let's print out everything. Okay, oh, it has to make a very big steps now. In the beginning. So next I want to print the current. Let's go the current difference. That would just be difference apparently. And we want to have a float for the current relative area. Still does need to cast. And then I want to print. Let's put the print at the bottom. And we print out also the diff. And current relative error. So that relative error is relatively big in the beginning. I think this is where my 0.07 comes from. And then in the end it's not that big. It even gets really, really small. 1%. Really small. And the max absolute value is still determined by the last thing. So very small relative error. Very small. Wow. Times a huge allocation is still a little bit bytes too much. But we definitely get progressively better and better. I don't think it makes any sense to try to approach this even better. Not really. That's good enough. Gubbins. Programming including basic and C. 40 something, 40, I don't think, 48 years. I cannot calculate. I'm senile, so I have to take my calculator. I'm 59, minus 12, 47 years. And then we have a function that very precisely and certainly larger is it a lower bound or an upper bound? Seriously, I think lower bound. What does it mean? I think it's an upper bound. Yeah, people want to have a reference, but I don't have one because it's my own formal. Yeah. No, also not. Okay, do it officially. Found by me. No. Dude, I don't know how to put it. I figured this out. So you have to blame me. Is that the right thing? All blame go to? Well, there is nothing scientific about it. Yeah, okay. I think we have that done. In larger than 1,000 or so. So result one, someone asks for 1, 2, 3, 1, 2, 3. So really a 1 billion. Up till 1 billion, I don't have more memory to test more. Well, I could add one more zero, but let's not do that. Then I want to see what these values are. But you definitely don't want to print everything anymore, I think. Or can we still do that? Yes, of course, we can still do that. Because this stays just 1,000 probes. Maybe we should do 10,000 probes. Let's add a zero here. And then hopefully that's still true. Yep. 30 kilobytes. What the f... This is way too precise. Scary. Scary precise. Insanely precise. It's even more precise than LLLE itself, I think. It seems. And here we are off by, well, 12. Never mind the relative error there. So it's off by less than, say, 1/10%. 0.5%, 0.6%. Keeps like that. Let's say roughly from here. Roughly, maybe you can do the 5 something. Then include the word roughly. No, it's still roughly that. So that's for 500 million. Dude, so incredible. So what? I send that, right? So 0.06%. Well, I was going to fine tune it, like maybe change this 5 into a 4 and then see if it gets better. But this is already so scary good that you wonder how can you impossibly get that good with a a constant like 1.6. I mean, if I change this in 1.61, what will happen? Are we gonna see something horribly bad? Like suddenly it doesn't work at all anymore? Because you would expect that. I really want to see this. Nope, it's not bad. Still not bad. It's not bad at all. It's almost the same. Actually, it's better. 0.004. No, wait a minute. I want to go to n equals 5. Yep, it's better. It is actually better. Okay, let's make it even larger. Crazy. Oh, even better. What the really? Oh no, I'm allocating 19 kilobytes too much. Completely insane. Yep. 0.03%. Well, I rounded off 204. And plus I have to go back to the bloody beginning of 5, of course. 500 million. There we are. Yeah, it's definitely 0.004 now. 0.04% ish. I'm gonna try this to make this a 3. How can this not have more influence than what it does? I don't get it. And better. Oh, no. No. Well, oh, wait, we are here. Yeah, 5. Then now it's a 3. Still a 3. I'm gonna go to the top. 0.6, oh no, 6.5%. That's a lot, man. I have the feeling can just subtract 10 bytes and then, or 9 bytes, you can subtract 9, and then this, well, okay, this starts to look like noise then. You can definitely subtract 9, it never gets below that. Yep, I want to have a minimum value as well. Mohaha. So do you calculate a minimum value and then do it again and then I don't know. The minimum diff. Okay, let's not exaggerate. The minimum diff is standard min of minimum diff and diff. And I want to print that at the end. Minimum diff is minimum diff. Eight. Wow. Ridiculous. I still have this 0.7, but it's ridiculous, of course. I want to rather see. Well, that's probably the good thing here, the most reasonable thing to look at. Yeah. I could do an average deviation, an average relative error for everything above 500 million or something like that. But well, too many statistics. I want to subtract that 8 just to mess with my formula. I'm doing +1 here, but hey, let's do -8. Min diff is now 0. Doesn't really make much difference, does it? It's still, yeah, no. Well, actually it does make a difference, yeah. It is now equal to, oh no, it's still 10 times larger. Oh, 100 times larger, I'm an idiot. 3.1% instead of, well, 7%, so it's better, but. So then we can do, let's say, I can calculate an offset. Well, I might do that here, but let's not do that here. Let's just do the offset here. So I'm gonna do NP. I'm gonna calculate that minus the min diff. Well, the second time around. So let's do this again then. I don't use the NG anymore, I just print everything. So we're gonna do, I'm putting nothing. Everything again. But this time we're doing well, it doesn't make sense to do that again because it's going to be 0 anyway. The rest is the same, and then we do NP minus the minimum diff. And we don't calculate the minimum diff, obviously. I'll print a minimum diff here. Here. Right, now I have that, and now I want to tune it. 15 kilobytes. So we go back to what I had in the beginning. That should be considerably larger than 15 kilobytes, right? 30 kilobytes. That's hardly larger, man. Let's try 3. Still 15 kilobytes. How can this not make any difference? Ten kilobytes. Some point I want to see an assert fire because it's really scary. It's starting to get scary here. Six kilobytes. That's impossible. That's impossible. And I really want to. I really need to see, but what the relative error is at the end. Because this is just 3%, just for the beginning. I need more statistics because this is really starts to be insane, absolutely insane. Let's say we have a double. Well, yeah, of course it is a double. Average relative error. Yeah. Average relative error for the last stuffs. So I'm just going to set it to 0, I think, and then we need a counter for. Oh, I know, counter. And then if if n is larger than half of this size, which is currently at the full blow thing. Well, I'm just taking that, or no, let's take the size. Divided by 2. Then we do plus count and add this to the sum. And then here we do average divided by the count. And I want to print it. Average relative error equals average relative error. For the last half then anyway. That's ridiculous. That's 0.01%. I'm onto something, I think. Who's going to believe me? Nobody's going to believe me. Maybe this is just 1/2. It has to be something like that. So then the 6/6 should even be better. Even closer to that. Columns. Okay, but there's some noise on it. Post Bunny, yeah, I'm way too late, but I'm onto something. I'm like making headlines here. Almost. Finally, the assertion failed. I think it's there is still some noise on it, and therefore we cannot approach to. We cannot approach 6666666. What was my last value? 5? I think so. Yeah. Let's try 5. Yo. Oh my god. That is absolutely insane. Hey, that is insane, man. That is insane. This error has become so small that it is ridiculous. You can probably do better. 6. (7.8) E minus 5. Night quadrants. Okay. I'm asking too much now. I'll leave it at 5. Although we can still play with this one, but it's like a nice number, isn't it? That's like 0.312 or something. Well, it's actually random as well. It's not really nice. 1 divided by 3.2. So we could try to play with this one as well, but it's already so insane that I don't even dare to touch it anymore. I think this is like it. Oh my god. Okay, let's try it again. So for the final. That. I don't know what's less than. On average, I have it on average. Is off. Just forget the average here. On average. And that would be minus E5. So that is. Yeah. 1, 2, 3, 4. And then I want it in percentages, so percentages. Hello, Poppy. I just made a function that is only 0.008% off. Not just any function, you know. I mean, what the fuck? And always too large. It doesn't make any sense. Really, it doesn't make any sense. Yeah, it probably does, but I don't understand it. Okay. Okay, well. You can't get it any better, I think, basically. Let's call it an upper bound. I'm still not, dude, what the fuck? Upper bound. I'm gonna have a chat with ChatGPT about this. A function returning an upper bound of the number of primes below n. Does that return a value that is guaranteed larger than the actual number of primes? A commonly used upper bound is that. However, this is asymptotic approximation, or not an upper bound. For a more conservative upper bound, use the Ross's theorem, and then we get that one. Yeah. And my function is way, 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 way better. But it was about upper or lower bound. No, it doesn't. Before it was like lower bound, so there was a different thing here. Probably that one or whatever. I'm going to go with upper bound. Calculate upper bound number of primes. Great, so now I can pre-allocate my factor, my C factor. No, not the C factor, sorry. I meant the result. I'm done with the knob. And with the number of primes. Uh-oh. Oh, whoa, 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 whoa. I don't know if it's called off. What was my offset? What was my... it's probably still on my screen, isn't it? I don't know. I'm not sure. And if it isn't, let me do the following. I'm writing this to write dot new. And then we leave the thing, and then we see that it is still on my screen. Min div is 5. I want to do now the following thing. Move new to that. Edit it. 5 is subtracted from it. So I have to subtract 5 now and add 1. So we have to subtract 4 here. And that then returns the number of primes. Yeah, that's the actual value, I guess, that I need. Let's keep checking it. So we don't want to have a resize. So I'm going to add an assert here. That the size is still equal to that upper bound. Fuck. Hmm? What? What? What the hell is this? I'm pretty sure that my upper bound is pretty good. Still, I don't understand that then. So if the upper bound gives a number of primes, which means that this prime is going to be less than 1 billion, right? So let's check that with the website here. The prime. It's slightly larger. Oh, that's that correct? Yeah, that's correct. So if you allocate the room for this many primes, then I can store all the way up till there. But I'm only going to store up till 1 billion, so it's a little bit too large. And well, 1%, 0.08%. So that's perfectly fine. And then someone explained to me why the size of result is like that is big. 100 mil. What is this? Yeah, wait a minute. Only 50 million primes. Okay, 50 million primes, and we have here 100. It's like twice as big. It's like exactly twice as big. There's a lot of zeros in it. Maybe some overflow somewhere. Oops. Probably not. It's really a serious problem. This must be larger than a little bit larger than 1 million. Yeah, so the upper bound is totally correct. So what's wrong with my result? I think I fucked up the code somewhere. So it's only zeros in it anyway. What the fuck? I have a lot of zeros in front of it. And then the prime numbers. Why? Oh, I'm getting it. Yep, and that's why it doubles it. Oh, I'm so stupid. Why am I so stupid? Bugs Bunny, I'm so stupid. At least I get it now, but still. Sad face. This is the so and so many time that I have done this. Like really. And now it's still Gordums. No, 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 we won't accept that. Totally do not accept that. I'm feeling stupid. But it still doesn't work. Size of that. Upper bound. Oh. Equals. Oh, yeah, see, but a little bit less stupid, but still stupid. Yeah, okay. Great. So that worked. And did it speed things up or not? We can not test that. I think it's slightly faster, but I can only remember the time of the with optimization. Try that one again. And the release one was 2.66 seconds. Restore, configure, make, run. Well, that's a very, very, very minuscule, but it is even more minuscule. Come on, less than? Nah, hardly any improvement. But okay, we had to do it. Accurate pre-allocation. The next step is that Let's see how much time everything takes. If I don't do this, then I think we are just almost done, almost immediately done. This is allocating the C, filling it with ones, and freeing it, which is quite a lot. But it might be, yeah, that's fucking 3 milliseconds. So how it does this memset in 3 milliseconds is beyond me. But definitely all the time we are spending here generating these primes are spent in these two loops. And I wonder how much time is spent in the second loop. It might even be the bulk of it. Wait, I meant of course and to comment that one out and not this one. No. Well, it's less than half of the time. 2 seconds in the first loop. And then one, how much was it? 2.5. 2.6. Yeah, 2.6 seconds. So 2 seconds in the first loop and only 0.6 seconds in the second loop. Well, this is not that much. Well, it shouldn't be. Now, something that I really don't like about this loop is that it does a test all the time for the max value. I think it will become a lot faster if I don't do that, but then I might overshoot it a little bit, which then might again result in an extra primes, which is maybe not that bad, but let me see how much faster it gets if we remove the test. So this is 2.6. And if I just don't do this test, oh, well, I need a test. I need some test. No, I can just do, you just run over the whole loop. Okay, run the whole loop. So 2.5. So it went from 0.6 to 0.5 seconds, that loop, just by removing the test. And how much time is spent in this thing here? So if I don't calculate anything, but now it might be optimized away in the sense that it just doesn't even do the loop anymore. I'm not sure about that. Well, let's see. Still almost 2.5. 2.4 each, but a little bit more. So it does not really spend a lot of time, apparently. Yeah, even 2.5 again. Apparently it does not really spend a lot of time into the receive index to prime function. I mean, it's like we did win less than removing the test, it seems. That's a division. And 2 multiplications and a lookup, table lookup. Nou ja. Right. Let's test something else. I could leave this out, but must be a better way. I can just start at the end of the sieve and find out where it is. Yeah, let's do that. Next prime, next prime, next prime. No, whatever. Is that -1? And then while not prime, or the prime itself calculated back from next prime minus sieve. Is less than or equal max value. Minus next prime. So after this loop, last prime, I'm gonna do a while because it looks a bit weird. Is while that so if it's not a prime, then we just continue until we find a prime. But we also continue if it is still larger than the max value. So afterwards, it is both prime because if we get here, this is false. It means that this is false and that is false. Which means that this is true, which means that it is a prime. So it is a prime and, well, a prime that is not larger than max value. So less or equal than max value. And therefore this will never be true if we just continue all the way up till last prime. And I don't have to test this. There, set 2.6 something. No, I didn't gain anything. It's not possible. That's not possible. This loop cannot take any time. So we comment this one out. Then last prime becomes sieve plus sieve size minus 1. And then the less than or equal is the same as next prime is less than that, which is what it was. And that was 2.5 seconds without the test. Two point five. Totally 2.5. Oh, that's impossible that this loop takes 0.1 seconds. Possible. Unless my sieve is like way too big, but that's ridiculous. It's not the case. I want to know how often I call this. So that it would be that minus value. Doesn't print anything because no debug output. $23. The 23 is like, yes, small-ish, totally small. That's what I expected it to be. Expected it to be that small. And now we are 2.6 seconds using debug output. What? No optimization. What's going on here? No, wait, that's not true. It's still with optimization. How on earth can it go from 2.5 seconds to 2.6 seconds? Well, when I added a loop of 23. Impossible. Absolutely impossible. So I don't do this, it was 2 seconds. And if we do that, but not that. Now that's better. This is even smaller than that one. So it does not take any time, okay? This does not take any time. That's impossible. And this does. And then removing the test didn't even do anything. I have no idea what this is, really. Anyway, let's try to speed it up as much as possible. Sieve index, minus sieve. Okay. The compiler should already do this optimization, of course. Need to address anyway. I need to address maybe more often than the internal stuff here. So this looks like really fast. We have an address and we check the contents. Cannot be much faster. No. And once we have it, well, then we need to know the difference, but it's relatively fast, I would say, just a subtraction. Per prime, we have to do the pushback as well, and we have to do this calculation. There's no way around it. I don't think this can be done any faster. And this, of course, doesn't make any difference, but well, let's make it shorter. At most got slower. This is so amazing, this. Yep, I have the feeling that we are missing out on some optimization or something. But why? So maybe something else I can do. I know for a fact that at the moment that next prime equals last prime, that this is true. So theoretically, we can do that test inside this loop, which should be slightly faster. Yep, and then I don't have to do it here. Let's see what that is. A little bit faster or not. Hardly. Please, we got below the 2.6 now. I don't know. Gonna leave it at this, I think. Right. And then this loop takes 2 seconds. Well, I don't think we'll ever run into this, because there's a break here and that's gonna happen way sooner. I'm going to remove this. Didn't do anything. Didn't do anything. Yeah, this is slow. Looks almost the same as that one. Let's just remove it. And this is more or less the same as that. Push it back here. That is a prime. Nah. Let's reintroduce the prime at least. So I can do prime is that. And then we just push back prime. I do the same thing here. And this is, yeah, this is the real slow stuff. We have to calculate this as part of the algorithm. Compression repeat times prime. The prime is just calculated. No way around that. I also have to run over all columns. Also part of the algorithm. Nothing we can do about that. And then this loop here. Int is call plus compression. Call plus compression. That's a multiplication here. But that was just calculated as an absolutely horrible thing with a lot of modulos. No, that should be able to do that one faster. For every prime we do this 8 times. Wow, that's like, well, every prime below the square root of. But it's still a lot. I think it's getting too late. I'm going to bed because it's just too late, and I'll try to optimize this further tomorrow. I assume, right? Fix me optimize this part loop. Check if it still works. And there I was hoping to get it under 1 second. If I get it under 1 second, I have one. Well, that's not true. But it would be. It's like 50 million. Yeah. Let's look at this number. If you 1 over this number is 1 nanosecond. It's now 2.5 nanoseconds per integer to find all the primes. Well, okay. So actually one other thing I would like to do, just, you know, because it's fun before I go to bed, and that is setting this value to a different value. If I make this 2, it should still work. And be slower, hopefully. That line should definitely be the same. Please work. I'm so happy. Oh, that is slower. But almost nothing. Seriously. Not almost as fast. Now you gotta be kidding me. This is no fun. This is absolutely no fun. I put it at 4. Now you're gonna say it's going to be slower. Oh, that's significantly faster. That helps at least. Let's start a compression of 5. .8. Yeah. It does get faster. And it goes wrong. No. Why? That's not the same number as there. At least this is still the same number. But the last one, no, that is not correct, man. I think I know what this is. I don't have enough small primes. No, that's ridiculous. I think I have that. It cannot be it. Compression 5 is failing. Why the hell is it failing? But this was still working, right? Should never have tested it. Now I can't sleep anymore. This is still working. Yep. Okay. Good night. Good night, Post Bunny. Thank you. I'll see you tomorrow.